one looks at the broader landscape here, we have a significant amount of CO2 emissions. CO2 that comes from burning fuels, CO2 that comes from, for instance, the production of cement, the production of ammonia. And this is a feedstock that we don't utilize. We generally just emit it into the atmosphere. And we hope that if the world is a large enough pot to dilute things into, that it isn't a problem. But we know that there's great scientific consensus and increasing societal recognition of the fact that the world just isn't an infinite dilution reservoir. That we need to find ways of either mitigating CO2 emissions or just avoiding those emissions altogether. And so, one could either sequester and store that CO2 or make it into something. We're advocates for making it into something, because if rather than just hiding it, you make it into something, you then have something that has value that you can then use to monetize that process of capturing. Since capturing isn't free, capturing does require doing work. It's much easier just to let it go than to hang on to it and do something with it. And what we're interested in particular is taking carbon dioxide, taking water, and taking electricity, combining these to make fuels or to make chemical feedstocks that then go into making plastics, things that we deal with in our everyday lives. So closing that carbon cycle is a big part of what we're looking at, and catalysts, as I mentioned earlier, feature very prominently in that work. That if you want to find a way of taking CO2, anchoring it onto a catalyst surface, breaking those carbon-oxygen bonds and replacing them with carbon-hydrogen bonds, you have to first have a very fundamental understanding of that reactivity, and then also understand how that small molecular level reaction fits into a much larger macroscopic reactor. And so we sort of pride ourselves as a lab in our ability to look at multiple length scales, not just the molecular level phenomena, but the large-scale continuum phenomena, how things flow into reactors and flow out. And as a chemical engineer, we feel well positioned to look at both the molecular level and larger-scale phenomena that are needed to make something like this a reality. And so when one looks today at the small rise of fuel cell technologies that we're seeing, right? Companies like Toyota have put out the Mirai, Honda has the Clarity, Hyundai has their own fuel cell vehicle. We've always had this chicken and egg problem with fuel cells, that no one wants to roll out refueling infrastructure because we don't have cars that run on hydrogen, and no one really wants to roll out the cars because there isn't the fueling infrastructure. Nonetheless, we're seeing this transformation take place. What we're hoping to do is leverage the very core technology of the fuel cell to enable these electrically driven transformations. A fuel cell takes in hydrogen and oxygen, creates water, and because that process is spontaneous, you get out electricity. If instead you were to put in water and put in electricity, you could then split the water to make hydrogen and oxygen. And that's basically what we're doing. We're putting in water, we're putting in CO2 as well, and breaking bonds and reforming new bonds that contain fuels. So it's just a fuel cell in reverse. And so by leveraging this technology that exists out there, we feel that we'll be able to get on a sort of learning curve for a CO2 electrolyzer more quickly. And that's at the very heart of the technology that we're working on right now. If we were able to make a CO2 electrolyzer, we would have this ability to convert CO2 into products like methanol, into ethylene, into propylene. If you make methanol, that methanol could then be made into formaldehyde and make its way into paints, into plastics, into resins. There are a whole bunch of different products that come out of that. The ethylene goes into polyethylene, which then makes its way into plastic bags. Similar sorts of routes for polypropylene. So the CO2 is really just a disguised carbon source. You then take that carbon and it becomes virtually everything that we deal with in our everyday lives. And so it's a way of re-envisioning our chemical feedstock pipeline. If you were to ask people a century ago, would we be running around digging holes in the ground and pulling the substance out of the ground that would then become a large part of what we see around us, people would have probably questioned that vision. It's very clear that it had legs, because gasoline is a very energy-dense carrier gasoline is a very energy-dense substance. But what we know and what we've come to learn is that there are challenges that come with that as well, with global warming, right? We want to take the advantages of something like gasoline, but be able to avoid the CO2 footprint. And the best way to do that is by taking the CO2 that comes out from burning the gasoline and making it back into gasoline, And so the CO2 electrolyzer enables this paradigm in which you can close that carbon cycle, so you maintain all the advantages that exist to a condensed fuel like gasoline or diesel, but avoid the CO2 footprint. And that way all our infrastructure becomes useful too. We continue to use refueling stations, use our existing cars. We don't just decide to cast these things away, which would come at enormous cost to society if we did decide to just do something entirely different. Yeah, and so we interact with startup companies and with larger companies as well. Some of this is through MIT's Energy Initiative, which has helped to foster many of these connections for us, and with people that we've known over the years that have sort of shared in this vision and see that this is something that could be big in a decade or 2 decade time frame.